Good morning. So it's a pleasure to be here. So thank you for the introduction. I have been to Brazil many times, and every time I come, I enjoy my stay here. So in this talk, I'm going to just give state of the art, the current state of affairs in this field of graph pattern mining. So I'll describe what the problem is. What are some of the common approaches that have been proposed, some of the algorithms, the efficient algorithms behind the notion of discovering these structures. And then I'll conclude with some future trends. And as Professor Mehra already mentioned, currently, so I am actually a professor in RPI, that's in upstate New York. But currently I'm on a sabbatical leave at this QCRI, which is the Qatar Computing Research Institute in Doha. And I'm sure many of you know of this place because they'll be hosting the World Cup in 2022. And I'll have more to say, a little bit more to say about QCRI towards the end of my talk. So in terms of what I'm going to talk about, so I'm going to start out with this description of what is graph mining, why is it important, what are some of the methods that we use, and then I'll actually go on to some other things I don't mention here, so approximations and so on, and what are the future trends in this area. So actually this field of frequent pattern discovery is actually something that has its origin in the, I would say, early 90s. And of course, people have been doing this kind of thing even before that. So at the very basic level, it's a search for commonly occurring things. Okay, what are the frequently occurring patterns in a given data set? So the classic example is people go to the supermarket and they buy a bunch of things together, and you want to look at, okay, what are people buying together? And a modern example of that would be Amazon's recommendations. So people who buy this book also buy this other book, and so how many customers, how many people are doing that? And then of course you can take this to much higher levels, so this is just sort of co-occurrence, right, whether two things co-occur together. And then as we all know, with the advent of bioinformatics, you can even look at the patterns in our genomes, so are there commonly occurring what we call motifs or frequent patterns in the human genome, and you can compare with other organisms. And then of course we are in this now a very networked world, right? We are like social networks and all kinds of other data that can be modeled as some sort of interconnected graphs. Open linked data is a new terminology. Big data, where things are, again, there's the whole point is that things are interconnected, and in this space you start looking for frequently occurring subgraphs. Okay, so things that happen together among, maybe in a social network it would be, are there groups of people with similar characteristics and they form these communities, right? So the discovery of communities is an example of some kind of a frequent structure discovery. So that's actually the motivation for this field of graph pattern mining. So given a large data set with all these connections, you can do lots of things with it. And one of the problems is this motif discovery problem that I just mentioned. And of course, so this is why graph mining, and I think this doesn't need any explanation. It's essentially that these days, no matter which area you want to talk about, whether it's science or business or the social realm, things are pretty much they have a rich structure, and whenever you have this kind of rich interconnected structure, you want to discover hidden relationships, hidden groups, and that's essentially the notion of graph mining. So these are classic examples of graphs. You have biological networks, social networks, physical networks like the internet, and of course things like chemical compounds and biological molecules can also be modeled as graphical structures. And anyway, I'm just going to skip over this. It's essentially emphasizing what I already said in words, that many data sets that don't appear to be graphs can actually be modeled as graphs. So the point is that traditionally, if you think of how we analyze data, essentially you think of some sort of a tabular structure. You're measuring some things about some objects and some properties, and you had this assumption. If you look at the statistical inference, that things are independent of each other. And suddenly when you talk about graphs, that independence assumption goes away, because now there's actually this connections between points, connections between objects, and that has to be exploited in any kind of pattern discovery framework. So there are many examples, and so I'm going to actually define the problem a little bit more precisely, and I'll show examples of what I mean. What is this graph pattern discovery? What does it actually mean? And I said there are lots of different applications, but so what we'll focus on is this notion of a frequent subgraph. Okay, and so this is the terminology I'll be using, and I'll be mentioning something called the support. And the support is simply how many times a given pattern appears. So the frequency of occurrence is actually this word. We use the word support for that. So we say a pattern is frequent if its support, that is the number of times it occurs, is above some threshold. Okay, so you have to set the threshold of what you consider to be frequent. So this is something that a user would determine, and then you have to go and discover these frequently occurring structures in your data. And here's an example of a chemical data structure, right? So here I'm showing 3 different chemical compounds, and I'm also showing some examples of patterns you might discover. So this this ring structure over here, for example, is something that appears in all 3 of them, and so that's a frequently occurring substructure in this set of compounds. And you can imagine how you might use this. So this could be used, for example, drugs that target a particular disease, or whether drugs are toxic or they are not toxic. You can try to discover, are there characteristics of one class of chemical compounds versus another class of chemical compounds, and what are the frequent structures within those. And of course graphs can be more complex. This is some sort of users going through maybe on a given site, or doing some commands, and what is the sequence in which those commands happen, right? So this is a directed graph, and again in this you can discover structure. So you can have very complex data sets, and one thing to note in mind is that each of these if you talk about a real life data set, right, you're going to have attributes besides the graph structure itself. So the graph structure basically says whether 2 things are connected, whether there's a direction between them, but on top of this you're going to have for every, let's say, vertex, you're going to have maybe attributes. What is it that makes, what is that what is that vertex, what are the properties of that vertex. And then of course edges can have attributes. So maybe what is the role being played, like what is the relationship between 2 and 3. So you're going to annotate these graphs with these labels or attributes. So and of course then you may say, why stop there? You can have temporal graphs, you can have time series. We know that things evolve in time, maybe things evolve in space, right? So you can see the problem is actually very complex, and it's as complex as you want to make it. So you can add all these dimensions, and you can try to mine the whole structure, and it's an unsolved problem actually. How to efficiently take these rich sets of attributes, this whole field of, again, different people are coming at it from different contexts. So you can think of this as, if you're aware of the semantic web concept, where people are trying to add ontologies and very well defined concepts, and what are the relationships, and then given such an ontology and the underlying data, can you mine? So in some sense the problem you're trying to solve is like the holy grail of search, the next generation of search, if you will, because now you do Google searches based on keywords, and you can't even ask simple questions like who was the president of the US in this year, and is there any relationship between the founding fathers, so of the US and the modern presidents. Simple questions cannot be answered today, and I think it's actually a great opportunity for computer scientists to actually help enable these kinds of searches. Those are intuitive questions that humans want to ask, and unfortunately the current technology doesn't allow you to do that. Okay, I mean you can only do this in a piecemeal fashion, like keyword, and then you try to infer things. So this is a very vast and open field, and it's a a great opportunity for us to make impact in the world. And you can imagine that those kinds of questions are very important for science, right? So you're collecting data, and you want to ask questions. Biologists want to ask questions about all this diverse sets of data. Astronomers want to look at these digital sky surveys and look for interesting objects. So the applications are vast. So coming back to a little bit more concrete setting, let me actually jump to the more graphical version of this explanation. So as I said, the field is vast and you can do lots of different things, but I'm going to talk about a specific problem of this pattern discovery within this vast area. So the basic problem is this: you are given some data set of graphs. So in this case, it's a small toy example. You have graph 1, G1, G2, and G3. Okay, 3 graphs, and they're labeled, right? So A, B, C, D are some attributes that are put on the vertices, and your task is basically stated here. Okay, find me the frequent subgraphs, okay, patterns that appear frequently in at least 2 of the graphs. Okay, so support what we call minimum support. What is your minimum threshold for anything to be considered to be frequent? Say 2. So I'm looking for patterns that appear at least 2 times. Okay, if they appear 3 times, great, but they must appear at least twice. And then the word maximal basically says that I'm looking for the largest such pattern. Okay, so there's no point giving me like A, right? A appears in all 3 graphs, but maybe it's not so interesting. Okay, so it's just a single node. So I'm looking for larger structures. So maximal means give me the largest such patterns you can find in terms of containment. Okay, so whether one subgraph is a subgraph of, one graph is a subgraph of the other. So find me the largest structures, and so the output would be one of the patterns is this one, because it appears, I'm showing the embedding. So the red nodes basically show how does this pattern appear, and it appears in at least 2. So in this case, exactly 2 of those. And here's another one, which is also the largest or one of the maximal patterns, and this also appears in those 2 graphs, right? So the task is simple, at least simply stated. Mining it is discovering this is a separate question. What is the complexity of the problem? I'm going to talk about that. But that's the problem. So you're given a bunch of structures, and go find common motifs, common patterns in this data set. So this is a variation, what I call database of many graphs. Okay, so this would be an example where I give you chemical compounds, or I give you protein structures, or I give you maybe your personal social networks, right? Your circle of friends. So if I give you those instances and I say, okay, are there common patterns in your common circle of friends? This would be an example of that. The other variation of this problem is what I call mining from a single large graph, right? So this is an example of, let's say, if I take the Facebook graph, it's just one single graph, maybe disconnected, but it's kind of like the friendship network taken as a whole, okay, globally. So now you have this one single graph again, and now I'm saying, okay, find me again all the frequently occurring subgraphs. And now the thing becomes a little bit tricky, because you have to count all the occurrences, right? So in a single graph, see in the previous example, I could just go and count how many graphs. So if I take this pattern, I can say, okay, it appears in G1 and G2, so the support is 2, right? Here, there's only one graph, so I can't just do number of graphs as not the answer, but it's like the number of ways I can embed something. So what we call the number of isomorphisms of that pattern. So as an example, if I take this pattern again, and I say, okay, how often does it appear? So here's a small demo of how many times it appears. 1, 2, 3, 4, 5, 6. So actually those are those are what I call the total number of embeddings. So how many ways can I match this guy? And matching is isomorphism, right? Subgraph isomorphism. So all the labels should be exactly as they appear. all the edges should be, all the connections should be preserved. So the total number of embeddings is 6, and then you can do some variation of that. You can say I want to do maybe no two edges should be in common between these embeddings. So that's what we call edge disjoint frequency. You can do vertex disjoint. So what is the largest number of occurrences that do not share any nodes in common? That would be the vertex disjoint variation. And by the way, this turns out to be an optimization problem, right? So because now among all the possible embeddings, they have to choose a maximum number of edge disjoint or vertex disjoint, and so it's actually an NP-hard problem to do that. So anyway, we'll have more to say about the complexity. So those are so let me just go ahead. So those are the two variants of the problem. Okay, either you're given many graphs and you want to find something, or you're given a single graph and you have to find something, and this makes it a little bit more complex because you have to actually enumerate all the possible ways in which you can match. All right, so how is it done? What is the state of the art, or what are some of the typical ways? So I'm just going to give you a highlight of the approach, and then I'll dig a little bit deeper into some of the well-known techniques. So here's the basic paradigm in pattern search, and the paradigm is that you have some bound, right? So this is you need something to be appearing at least twice. And so we are going to use this bound, this minimum threshold, to prune things. So it's basically just a search based on some pruning on this criteria. And so how should we approach this? And the standard systematic way is I'm going to grow bottom up. Okay, so I'm going to basically start with single edges. I'm going to check whether the edge is frequent. If it is, I'm going to extend by adding one more edge to an existing graph. And then I'll keep on doing this recursively. Okay, add one edge at a time. And of course, this still gives you a lot of flexibility. You can do a breadth first expansion, you can do a depth first expansion, you can add all kinds of optimization and so on. But just the basic paradigm is that we start with as an example, in a given. So this is the variation where you have 3 different graphs, and I want to find the frequent things. So what I call, you start with the frequent edges. Okay, so pick any edge, count how many times it appears. So here, for example, AC is one of the examples, right? It appears in 2 of them. So graph 1 has an AC and graph 2 has an AC. So it appears at least twice. And of course, AA, AD, BD, these are all frequently occurring things. But I'm just showing you, if I choose AC as my starting point, how can I expand it? I want to add one more edge. So the one more edge you can add either to the C, right? So you're just making a linear chain, or you can actually branch off from the A and you can add one more edge from the A. So this would be the example where you have so these are actually all the possible next what we call candidates. So given a frequent pattern, I need to expand it by adding one more edge. In this simple example, these are the only 2 topologies that you can have. Okay, so either you add an extension off of the C, but any of the labels can be chosen, right? So A, B, C, D are all viable options to be extended with. And likewise, you can either, you start from this node and you can add the extension, and then all possible extensions can be added, meaning all possible labels can be added, A, B, C, D. Okay, so that's what I call the next level, starting from this node. You do the same thing for the other guys as well. But let's just focus on this for the time being. Now, what we should do is we should of course remove patterns that are not frequent, right? So then you start throwing things out. So now you have to do the following. You have to take a pattern, and you have to basically count how many times does it appear in my data set. And so this is an example of subgraph isomorphism. So I have to actually do a very quick isomorphism checking and see how often it appears. And so what will happen is that you're going to start throwing away things. So it turns out that these guys, it's not frequent, that's not frequent, that's not frequent. It doesn't appear 2 times. That one does, by the way. The ACA appears 2 times, and you can check that it should be, hopefully, yeah, CAA. So that's another way of thinking about this is that you could, you have to do subgraph checking. So this could be AAC or ACA like that, and it appears in that top left branch is AAC is exactly AAC, and likewise you have the AAC in the second graph, right? So this appears 2 times. So you have to do the isomorphism, subgraph isomorphism for getting that, and you get the picture, right? So then you have the thing that survives, you can extend them even further. Okay, and I'll have more to say about how to do the extension. So the idea is that you want to extend, but you want to avoid duplicates, and you have to get into graph isomorphism for that. So this then becomes the frequent patterns that from AC. You have to do the same thing from the other guys. All right, so that's the basic paradigm, and as I said, there's still scope for a lot of algorithmic tuning and enhancements. But here are the basic 2 challenges that we have to have. Okay, so if you are going to enumerate things, you have to make sure that you don't have duplicates, because there's no point because this is a graph domain, and the same pattern can be obtained in different ways, and so there has to be a very quick way of checking whether 2 graphs are isomorphic. Are they matching in topology, in terms of label? And actually right now we do not have a polynomial time algorithm for graph isomorphism, right? But I think people conjecture it's in P, but we don't have a polynomial time method for it yet. So maybe there is hope there in terms of at least the complexity part. But there's actually a much bigger challenge in front of us. We have to not only do graph isomorphism to remove duplicates, we have to do subgraph isomorphism to count, right? So whenever you have a pattern, I need to know how many times it appears. And obviously this problem is known to be in NP, right? So I mean it's NP complete. So that's the 2 challenges that we have. And on top of, so this is actually just to show why you need isomorphism checking, because you can easily have the same pattern can be obtained in 2 different ways. So I can take the AAC and I can add a D to that to the middle A, or I can take CAD, which is a different pattern, right? But I can add an A to the middle A, and actually these 2 graphs are exactly the same graph, right? So when you do extensions, you don't want to be counting the same thing over and over again. So that's why we need graph isomorphism to check these. And then like the other problem I mentioned is even harder. So given a pattern, you have to do subgraph testing against all the graphs in a database. Now imagine you have a database of 1 million graphs, which is not uncommon. I mean, if you have chemical compounds, you can easily have millions of these chemical compounds. Okay, they are granted they're small. Compared to social networks, chemical compounds are not that big. But still, you have millions and millions of those, and you still have to do the subgraph isomorphism checking very fast. So you have to check whether am I in G1, am I in G2, maybe not, and so on and so forth, right? So you have to do this over and over again. It's not just that you're doing it once. Every time you extend, you check, right? So that's actually another opportunity for optimization, because it's not like we're doing isomorphism from scratch every time, right? So because that would be very expensive. So every time if I had to do the isomorphism without any knowledge, that makes things much more expensive. But I can use, because I know I've already done the isomorphism for a subgraph and I'm adding something. So it's like an incremental isomorphism checking, right, in some sense. So that has potential to be done much faster.